So welcome back to Mobile Communications, the Q&A session covering today the remaining parts of wireless LAN plus Bluetooth, etc. So what is left from wireless LANs? It was about management. So there were many things about how to synchronize networks, how to perform power management, because most of the devices are battery driven. So this is why this kind of management is quite important. We saw these interesting wake and sleep patterns where stations wake up, listen for some time to a signal, and then go back to sleep. And if there's data, they stay awake, and then they can take over data, and they have a so-called power saving poll where they say, okay, I'm awake now, please send data, and then the access point can send data to the station that is awake for a certain time. We also learned that there are other versions how you can do this, and this is also related to one of the questions. I showed you as well now the newest standard, the 11AX, marketed as Wi-Fi 6, or also 6E, if you have additional the 6 GHz band, which is not available in Europe so far, will be soon available in the US. The chips are there. The big advantage, you see many non-overlapping channels. So that's really a big advantage. Okay, so coming to the first questions. Well, one of the tasks when talking about the IEEE standard, you see, okay, usually I use the term 802.11, that's the standard based on IEEE, and then we have the Wi-Fi Alliance, and they do more the marketing, compatibility, and they pick some parts of the standard and then say, okay, this is what we need for wireless, multimedia, mobility, etc., etc. So that's just, if you read these acronyms, these terms, that you know, oh, okay, this is Wi-Fi, this is the Alliance, this is marketing, oh, this is the standard. So first question, I talked about synchronization. Why do I need some synchronization? Because for normal data transmission, well, there's no synchronization, well, not really needed. You know the MAC access scheme. So why do we need synchronization in a wireless LAN? Now, why do we have to synchronize the stations? So synchronization. Why should the stations know the time? Yeah, so if you sleep, and you know, you have to know when you have to wake up, because the synchronization is, among other purposes, it's needed for this wake up pattern, because otherwise, when should you wake up? You sleep most of the time to save energy, and then you wake up, and then you will receive the data, and you will receive, for example, this traffic indication map telling you, oh, there's data waiting for you at the base station. Otherwise, you have to stay awake all the time, and this wastes energy. So synchronization is needed to have these nice wake and sleep patterns. But if we have these patterns, there are also some negative effects. Think of what happens if you are sleeping. What are negative effects of power saving? Think especially of trade-offs, power consumption, and certain quality of service. Higher latency, exactly. The problem is, if you have these power saving mechanisms, and if they do not really match your application, it can happen that the voice quality is really bad, and you will really notice it, this wake up patterns. So how to guarantee certain delays if the stations are sleeping? So that's really a problem. And so this was a big problem, and this is also one of the reasons why this new scheme has been developed, this advanced scheme that basically works a bit different from, it's called the automatic power save delivery. Remember, what is the basic idea there? So it's not this kind of, well, you wake up periodically, but you basically flip the roles. So why is this maybe more efficient for certain applications? This it's called power save delivery, but what is the idea there? So in the classical scheme, the stations have to wake up in a synchronized fashion, all the stations, and then the access point can transmit basically this traffic indication map telling the stations, okay, I have some data for you. And then the stations can go to sleep again if there's no data, or transmit some data if there's data waiting. But what is the idea of this APSD scheme? And this is what your stations and your access points know how to handle this. So the idea there is we do not have this wake up pattern anymore, but the station, in this time, the station, not the access point, wakes up and sends some data, acknowledged by the access point, and then the access point can send data back. So if there's data waiting at the access point, well, tough luck. The access point has to wait until the station wakes up. So the applications on the stations, they trigger this waking up and checking for data. And this is ideal for voice over IP, where you have, each 10 milliseconds you send data packets from the station to the access point. And if you send something, okay, there might be also data in the reverse direction. So that's ideal for this voice over IP setting, where both sides send or exchange voice data. And this is what you can use for different applications, because the applications on the stations, they know how often they need data. So basically they reversed the roles, so it's not the access point telling the stations, oh, I have something for you, and this is why the stations have to wake up periodically. Now for this APSD, what all your stations know how to do it, the stations wake up as soon as the applications tell the stations, I have to send something, or please check for data. The idea is that the application knows best when to wake up. If it's a video application or an audio application, so the applications know that, well, I should receive new data every 10 milliseconds, then I better wake up every 10 milliseconds and check for new data. So that's the idea. And this is the way more advanced scheme, this APSD. And this is why this is also the scheme implemented in all the devices to support this wireless multimedia. So the question is the standard for power saving on the access point side? Usually no one cares that much for the access point, because you say this is attached to the mains anyway, so you have enough energy. But indeed, it's the case that if there is no traffic and no one wants to reach the access point is basically in a kind of a receive mode, waiting for data, and this saves a lot of energy. So the access point is not permanently sending something. The access point is sending a beacon from time to time. So this is why the access point has to wake up from time to time. So every second or whatever you send out the beacon. But there is not a explicit mechanism like this power saving for the access points. Because, well, you say, okay, it's connected to the mains. And this also, by the way, a reason that you cannot cover huge regions only with wireless LANs. It would waste too much power. So there is some power saving, but not this kind of explicit mechanisms like this APSD you have for the stations, because they are battery operated. Okay, we also talked about roaming. So roaming really costs a lot of time, and that's a problem if you have a connection, a voice over IP connection. So you might hear it compared to mobile phone, for example. How to speed up? That's built in, these mechanisms are integrated in your smartphones, and this is why they are quite fast. So can you roughly say why does it cost a lot of time and how to speed up? So you don't have to know the standards or whatever, but what is the idea? Why does it take for some time? You just move through the city and then think of, okay, seamless roaming between completely different wireless LANs. Why does it take that long? Authentication, yes. So it takes a while until you receive a beacon, and then you have to perform what I showed you here without, again, going to all details, but there are many steps, and that's an enterprise network, just an example, many steps needed for authentication before you're allowed to participate. And this is why your smartphone follows these three standards, K, R, and V, all integrated now in the 802.11. So basically, what do? You collect roaming networks prior to roaming. So while your mobile phone, tablet, whatever, moves through the city, whatever, it collects potential roaming networks. So it collects the list permanently, a list of channels, a list of SSIDs. So the mobile phone or tablet scans all the channels all the time. So you scan if you receive some more SSIDs. So that's one of the point. The next point is that authentication can be done much faster. And the third point was that you can force a client to roam before the signal is too weak. So typically roaming in wireless LAN says, okay, as soon as the signal is too weak to one of the wireless LANs, then I check if there's another one. But then your connection breaks or your voice stream is interrupted. So why not forcing the client to roam if the system sees, so the access point sees, okay, you manage lists about access points and you can see, okay, there are better access points. So you can force the client to roam. So as soon as you see, well, this is a client close to me, for example, or the signal is stronger to another access point, but still there's a signal good enough to the old access point. The access points can force the client. So these are mechanisms that make the roaming kind of smoother, more seamless. And then in addition, this support for the authentication so that you can do this authentication faster than the classical way. So the classical way follows this 802.1x. That's also used for fixed networks and uses a lot of exchanges. So there's the standard tells you how to do this faster. So you see all these steps help to make the wireless LAN more efficient for, let's say, multimedia applications. Because otherwise you will see interruptions, etc., and that's a problem. The final question, I showed you briefly the newest standard, .11ax. The first products are there with extremely high data rates, so that's quite nice, going up to more than 1 gigabit per second per stream, and there are devices available that can handle more than 10 gigabit per second. That's quite a lot. So now think back, the basic idea was you had different stations and you had an access point, and we had basically these medium access mechanisms where you do the carrier sensing, and that's the idea. It's this distributed coordination function, and this is what the medium access control is based on. And then we added some quality of service by using different waiting times. And now we have this 11AX system. If you look at this, what is really left from these more distributed mechanisms? Is this really the old wireless LAN anymore? This is rather something to think about. I don't know what your opinion is, but if you read something that now it's a centrally controlled Mac, you do something like dynamic bandwidth assignment. You have resource units, that means time frequency slots. Yes, we use MIMO and all these nice things. But if you read this first item, you see this is not the classical wireless LAN anymore. Because now you have basically an access point, well, that's more or less kind of a base station like you have in LTE. It's not exactly the same, but it's still wireless LAN, used a bit different schemes. But okay, we also use now OFDMA, exactly the same as LTE. But this is not this distributed system anymore. Now we have a centrally controlled system, because in the end, during standardization, I guess everyone saw that, okay, if you want to guarantee something, you need some central controller for the network. Still, it is not as extremely controlled as an LTE network, because you may have your neighbors and all these things. But you see, what is left from wireless LAN? This is something to discuss. And we quite often have the discussions if wireless LANs will survive at all. Because, I mean, why not using LTE in the first place? Okay, there are only the 3 big operators, but you could operate your own LTE network. So why implementing different piece of hardware, standards, etc.? We will see in the future. So there are some people saying that we will not have wireless LANs anymore, just using LTE technology and 5G and all the things that will come in the future. I don't know. So we will see. Okay, so this is more kind of, well, not really philosophical question, but it's something to think about. Is this still this idea of lightweight wireless LAN? Are there any questions left when it comes to wireless LAN? So please don't learn these numbers and figures, just the ideas behind, the mechanisms. So why do we do some things? We do it like, for example, Mac, how we do it, this DCF, how it works, how medium access is handled, how we implement different priorities, so that you can compare these types of networks with, for example, Bluetooth networks. So are there some more questions? Well, the question is, should you change the Wi-Fi router if it's, in your example, 6 years old? Absolutely, if you want to have the new standards like 11AC, which is integrated, 11AX, we have to check for the new devices. If they really have the standards, then you need a new router. So if you get one of the new DSL routers, whatever, they follow the new standards. But if it's 6 years old, you will have an ABGN, so following the substandards. The former names were ABGN, so most likely it's this N standard. That is the newest one your device follows if it's 6 years old. So it will not have the AC and definitely not the AX, which is, well, only the very newest products will have AX. Very good question. Is it realistic to use these extreme modulation schemes? 1024. Not really. So yes, if you think of, okay, you have your access point in your living room and you have a line of sight to your many devices like a TV set, like a gaming console, like whatever you have there. Within one room, yes, you can do it. But 2, 3, 4 walls, many neighbors, this really will be a problem. So also in open space, you can do this. But in more realistic settings, we will see. But still, check the data rates here. So still, you come close to a gigabit per second per spatial stream, and then it depends on the device what you support. But only if you have these large channels, 160 megahertz. So this is why they go to the 6 gigahertz carriers, because otherwise you do not have 160 megahertz. So then maybe, usually we have something like 40 megahertz channels. 80, well, it depends where you operate. And then you see, okay, everything drops to this 200 something, which is already a lot, 200 megabit per second per spatial stream. And if you then have whatever 4 or 8 spatial streams, this then altogether already reaches this 1 gig and more. It depends on the device. But you're fully right. Usually you will never have in real settings go up to this 1024 QAM. I have my doubts because too much interference. Okay, so that's all about the wireless LANs. And then we had a look into Bluetooth. Bluetooth, I told you the very beginning with this very simple idea of, well, replacing cables and replacing the infrared. So this was this infrared called IRA. And so all mobile phones had this little window where you had the infrared, the LED, and then you could simply exchange things. From a privacy perspective, perfect thing, because very easy to shield. Our Bluetooth, that's not that easy to shield. Then I also explained to you that today's Bluetooth basically consists of 2 different pieces of hardware. One is the classical Bluetooth called basic rate plus an optional enhanced data rate, and the other one is the low energy. That's when you read Bluetooth low energy, you know, okay, that's a separate controller. You have the classical one and the BLE controller. Okay, and maybe additionally you can have something they call a standard alternate MAC and PHY. So that's simply a wireless LAN, for example. Wireless LAN piece of hardware can be integrated. So then I explained the classical Bluetooth system, classical Bluetooth, Bluetooth basic rate, enhanced data rate. So especially how you create a Pico network out of different devices. The key idea, having a master and up to 7 slaves. So that was the idea there. And then many different packet formats. That's not the important point. Also some of the data rates, just to show you what is the classical data rate shown here. So 400 something kilobit per second in a symmetric setting, or you can also have an asymmetric setting. The typical data rates for voice, because you want to replace the cable for a headset, so 64 kilobit per second. And then we have the enhanced data rates, and they will reach, well, as you see here, a bit higher data rates, 2 megabit per second. So that's the classical Bluetooth standard with the basic data rate and the enhanced data rate. So now when you compare what was in the early days the idea of Bluetooth and what do you have today? Early days I mentioned some, but what can you do today with Bluetooth in general? So it's not only the headset. What else do you think of when you hear, oh, it's Bluetooth or Bluetooth low energy? Wires for only short distance. Yeah, usually it's 10 meters. And the early times, it was really only for device communication. So keyboard to laptop, headset to mobile phone. Exactly, mouse connectivity. That's what you use the classical Bluetooth for. What else could you think of if you hear today with the smartwatch to smartphone? Ha, exactly, measure distances. You see, mostly low energy, but yes, collecting sensor data. Okay, now we come to the new applications. Exactly. The point is, it all started out as a communication technology. And as you mentioned, exactly with COVID, Corona, and fitness and sensors and all these things, you do more with it. If this works or not, that's still discussed. But you do more. Sensor connection now, exactly. Beacons for advertisement, exactly. So shopping centers use beacons for tracking, etc. Or the newest thing you can do is you can yes, you can find your phone from your watch, so that indeed is helpful. Plus, you can even do localization. If you hear this, now this should be a head, okay, and these are your headsets, earphones, and you have somewhere you watch a movie, and you can measure now exactly the angle in 3D between the device and your headphones. And if you turn around with the head, then automatically the audio is adjusted. Like if you were standing in a room and listened to music. So depending on where you watch, you will hear different parts of the music with a different whatever quality, etc., etc. A lot of signal processing, but this is something you can do today, or at least after software update for some of the headsets from some vendors. So you see, that's a lot more. Okay, let's go back to the basic Bluetooth. Yeah, live data streams. So exactly to sensors, etc. Bluetooth Low Energy. So I will come back to Bluetooth Low Energy in a second. So if we go back to the classical Bluetooth, if you compare to the wireless LAN, you should know at least the basic differences. Well, data rates, okay, they're different. That's obvious. But what else is different between classical wireless LAN as we use it and classical Bluetooth as we use it? Besides the data rates. Data rates are obvious. Megabits, many megabits in wireless LANs, only some megabits Bluetooth, or hundreds of kilobits. But what else is this? Internet access, well, yes, typically wireless LAN comes with an access point, and the access point then has internet access. But you could also use Bluetooth to connect to the internet if you have some kind of device that translates your data from Bluetooth into something that goes into the internet. So IP over Bluetooth indeed is fully available. So Bluetooth uses fast hopping pattern. Well, you have a hopping pattern, that's true, and it seems for us that it's fast because it's 1600 times per second, but indeed it is called a slow hopping because you transmit several symbols, or here many bits, using the same frequency. So although it's 1600 times per second, it's slow hopping. Fast hopping would be using different frequencies for the same symbol, or let's say the same bit, you will send it over many different frequencies. So, but indeed, you use hopping, frequency hopping. That's not used in wireless LAN. You stay on a channel. Absolutely right. The medium access, well, you have more spectrum in wireless LAN. You have here, for example, 20 or 40 megahertz. And Bluetooth, you spread it over the, well, 79 different channels. If you look at the services, besides the bit per second, what else is a difference? What can you do with Bluetooth you cannot do with a wireless LAN? You cannot really give hard guarantees in wireless LANs due to the MAC scheme. You have these priorities and waiting times, but in Bluetooth, you can guarantee, for example, 64 kilobit per second, because the idea is the master controls everything. I will come back to the advertisement and low energy then in the following sections. But you're right, there are no advertisements whatever in wireless LAN. But think of the basic idea of Bluetooth. There is a master controlling the slaves. And I will come back to exactly this setting, master-slave, also with the questions of what is a Piconet and why is there no collision in a Piconet? What is the basic idea? How do you set up a Piconet? What is it? The Piconet consists of one master and up to 7 slaves, right? And the idea is, and this gives you the answer why nothing can really happen, exactly only one device in a Piconet can transmit at a certain time. So the master controls the hopping sequence. So you're jumping through the spectrum. And this is controlled by the master. It's by the address and the internal clock, and that determines the hopping pattern. All the slaves will hop fully synchronized. And if you want to participate in a Piconet, and that's the definition of a Piconet, you have to be synchronized to the hopping sequence. That's it. And as only the master gives you the right to send, a slave cannot simply send. So there can be no collision at all, because the master controls, it's simple, it's a polling scheme. So you have this kind of ping pong between master and slave, and that's it. And as long as everyone follows the standard, nothing can happen. So only one device can send at a certain moment in time. So that is the basic idea. So there is no collision within the Piconet. But how can still collisions occur? Yes, there can be collisions with a wireless LAN, but how can collisions occur? Only using Bluetooth. Between Piconets, exactly. So if all of you set up your own Piconets, you will all jump in the spectrum, and then there might be some collisions. When you jump at the same time on the same frequency, there is a collision. So between Piconets, you can have collisions. So this is why sometimes this is called code division frequency hopping spread spectrum. So the code is then the address of the master, and then you spread this hopping over the different channels. Here the question is, what happens if a slave just not stops sending? Yeah, then the slave does not behave according to the standard. That's all. And then the Piconet is destroyed. But it's difficult because then you have to play with the firmware. So it's in the firmware of the Bluetooth modules, so you have to, well, change it. But indeed, well, that's it. Then you destroy and the master will not receive it, so you can destroy the network, but that's it. So indeed, that's a denial of service attack if you know the hopping sequence. You follow the hopping, and then basically you send only on these frequencies. Then you can perform a denial of service attack for a very specific single Piconet. Indeed, that's feasible. No. That's a denial of service attack, indeed. So that's what you can do. Anytime you can create your own Piconet. So if a slave says, I don't want to be slave anymore, the slave could say, could be controlled by software, I want to be a master. But then you have your own Piconet. So that's a new Piconet. And if someone wants to join, you have to join the hopping pattern of this new master, former slave. What you can do is you can jump back and forth between your old Piconet, you act as a master, and the new Piconet, you act as a slave, and a new Piconet, you act as a master. And while jumping, you can carry data with you, and this is one way of how you transfer data from one Piconet to another one. Devices jumping back and forth between the networks, and they can have different roles. They can jump back and forth as slaves, or master in one Piconet, slave in another Piconet. So that works. If two slaves want to communicate with each other, that was one of the questions, usually you have to go through the master. There is a way that the master can allow direct communication because the master controls the slots. Then you could think of the master tells the slaves, okay, in this slot you can directly exchange something. You don't have to go via the master. The normal way is always via the master. So the master controls everything, and this is why you can guarantee quality of service, because you can control the whole data transmission as the master by controlling the single slots. That's the idea. So you control the slots, then you know what's going on. So as soon as you start a new hopping pattern, you create your own Piconet. That's the idea. But that's an interesting idea for denial of service. You can actually cancel out a single Piconet. You know the hopping pattern, but then you send every time the master wants to send something. That's a good idea. Okay, so final question, enhanced data rates. How do you achieve higher data rates? The classical Bluetooth, the basic rate, that's this up to 720 something kilobit per second, maximum in asymmetric fashion, symmetric 433 in both directions. How can you go to higher data rates? Well, one thing we can always do, and that's done in the classical Bluetooth. So if you look at this slide, it will give you at least part of the answer. For example, the higher data rates here, they do not use redundancy, so there's no forward error correction. So as you see for the higher data rates, everything else is basically the same. So also for the higher data rates, you have to follow the patterns, jumping, etc. But what you do is, that's just a detail shown here. You go to a new modulation scheme, differential phase shift keying. So you use more points in the constellation diagram, so you can code more bits, and that's the idea. So basically, you switch from, that's the classical part, that's the header of the packet, and then you can switch to a higher data rate. Something similar we saw in the classical wireless LANs. For compatibility reasons, the begin of a packet is still the classical way how you do it, and then you can transmit more bits per second. So that's basically all you can do with the classical Bluetooth. There were some discussions for higher data rates, etc. But the problem is that many said, why having higher data rates, also this integration of wireless LAN, then go for wireless LAN. So I mean, if you need higher data rates. But think of, there's also competition between different parts during the standardization. Companies, they say, oh, we need Bluetooth for marketing, but then we have higher data rates, things like this. So Bluetooth, the name Bluetooth is well established, and this is why companies want to stay with this idea of Bluetooth. Okay, so I continued a bit with the classical scheme, how the transmission is done. Here you see this ping pong. The master controls and can set up, for example, for this connection-oriented transmission of voice. That's, for example, used for headsets to achieve the 64 kilobit per second. That's what the master does. And then the master also controls this sending data and asking the slaves if they have something to send. And it's the responsibility of the master to poll the slaves. So if the master does not poll a slave, tough luck for the slave. So the slave cannot do anything about this. So if there's no polling, yeah, the slave cannot send. So it's the responsibility of the master. That's the idea in Bluetooth. Okay, so well, we basically answered the first two questions. Can slaves send on their own? Everyone now says no, they cannot. That's the idea. And then the question, how can you guarantee certain data rates, certain delays? So that's all up to the master. We basically answered this already. So if the master pulls you every 10 seconds, well, then you can assume, okay, that's a problem with your delay, and maybe also the data rate is quite low. If the master pulls you whatever every this and that milliseconds, then you can have higher data rates. So the applications basically determine how often the master has to pull which kind of slave. So, but this is all done during this initial setting up a connection and attaching to this Bluetooth Piconet. The devices will tell what they are and what they need. And then the master knows the needs of the different slaves and has to behave accordingly, or tell the slaves it doesn't work. So I cannot accept yet another device. For example, if you have already 3 ongoing high rate audio streams, you cannot have a 4th one. Then the master will simply reject the request of a new slave. So this is how you can actually guarantee this. We looked a bit more into power saving, and this is this question about the sniff mode. So, well, what is the advantage of the sniff mode? How does it help reducing power? But what is also maybe a disadvantage of the sniff mode? Device sleeps and only listens for transmissions at an interval that is set by the master. So this is why I gave you from this old chip where we measured this, the sniff modes, they really save a lot of power. You see, there's a big difference. So less active, but also if you look at this example, you see both versions have the same data rate, but one uses only 1/8 of the current, so power consumption really goes down. So that's the advantage of sleeping longer, and the disadvantage is delay. If you look at one of the devices has this 40 milliseconds intervals, and the other one sleeps for 1.28 seconds. So if you do not care about the delay, then you can save even more energy. And you directly see this. This was one of the first versions of chips from Cambridge Silicon Radio, where we have the precise figures. So that's quite interesting to see. So the sniff mode directly influences the power consumption. The question is, do you have to re-establish the connection? You do not have to re-establish anything. So sniff mode, that basically means that you are fully synchronized. So the device is still synchronized to the hopping pattern and simply wakes up at the predetermined time and can immediately communicate. So there is no additional procedure needed. So you do not have to resynchronize. So this is not a deep sleep. And you see what happens if you're really in deep sleep. Then you go further down. So standbys, etc. But you do not follow the hopping pattern. But in sniff mode, you still follow. You hop through the channels, but you do not send anything, and you don't have to receive anything. It's just that you follow. Basically, you counter, well, continues, and you count or you calculate which is the next channel without sending, receiving, or whatever. And this does not consume that much power. To follow the hopping pattern, this is just a calculation. This is just, you need the address of the master and you need the clock of the master. And if you have both, all the devices, they simply continue to calculate the hopping pattern. From time to time, you have to wake up, indeed, because yes, there are problems like clock drift, etc. But these are details. So that's the basic idea of this sniffing. I also showed you some of the security features, and to be honest, if you look at the specification, 3,200 something pages, there are many pages about how to do the security, which algorithms to use. And indeed, you cannot go into the details here, because this would cover an own lecture of what kind of algorithms and advantages and disadvantages and all the different protocols, etc. So this is why I explained basically this core ideas of, and this is what you know from your devices, there is some pairing. This has been done in former times by pins only. Today you can use something like near field communication, so you hold two devices close to each other, or you use out of band, so that means you use different technology, or you enter some numbers, etc. And that was the idea. So you pair devices. That's different from wireless LAN networks. There you use this authentication mechanisms, as I showed you. Here you pair them, then they know each other, and they store internally a key. And the next time they see each other, you don't have to repair the devices. And this is why, for example, if you have a rental car, you see the names of all the smartphones of other drivers. So if they paired their mobile phone to the car, so the car still knows the mobile phone. So you better delete this list, because it's quite funny to see who else was in the car. Or this well for car sharing. So the devices know all the other devices that were paired. And for the next time you want to communicate, well, you can easily generate an encryption key for a certain session, and based on this you can then generate payload keys for the ciphering, the encryption of the data stream. So that is the core idea there. But as I said, the real system uses many more mechanisms, too much for the lecture. And the same is true for all the protocols, the options, the parameters. This is quite complex, and you should know one of the solutions to guarantee at least some compatibility. What does it mean? If you have a Bluetooth device, still today it's not guaranteed that it works together with another Bluetooth device. This is quite obvious if you have a keyboard, that you cannot send a picture to the keyboard. But for some other devices it's not that obvious. So what is the solution there? So in Bluetooth, it's not guaranteed that you have this kind of backward compatibility. So it's not the case that the newest Bluetooth device automatically follows all the old standards using different parameters, options, etc. You saw there are many protocols using Bluetooth. There's one idea Bluetooth follows to solve the problem. Profiles, exactly. So as you have so many different protocols, you have to say, okay, for this application, for example, advanced audio distribution profile, quite often used for audio, I pick this, and this protocol, I set these parameters, and I use only these options, and I drop this and that options, because some settings are optional, some are mandatory, etc. But then it's asked, okay, data rates and things like this, delays, and this is all set in these profiles. And then you know, if my device follows this profile and also the other device follows the profile, they should be able to use Bluetooth. Otherwise it simply doesn't work. So and this is why you have simple profiles like serial port, which is very helpful, because serial port you basically replace a cable. And then there are also more complex things like human interface device profiles and these things. So it's quite different what you have. There are many profiles available, and you see the link. So this is quite complex, and this is also different to wireless LANs. Wireless LANs do not standardize these kind of profiles, whatever. So they offer the mechanisms. Indeed, you can choose between mechanisms, but everything else is left to the applications and to the application programmers. And here it's integrated in the profile. So this is also software. It's in the software stack, which settings we use, etc. So you have a part of hardware, but also software. Okay, and this is why the standard is quite big. I remember the days when the standard was just some pages. That was the basic idea of Bluetooth. and today, okay, a bit more. Good. After these things, I showed you some of the versions, a bit of the history, and then Bluetooth Low Energy. Please do remember, this is not the classical Bluetooth anymore. Well, we could even say, okay, we kept the name Bluetooth for marketing reasons. It is a different technology. Yes, it uses some higher layers together with the classical Bluetooth, but yes, it operates at the same frequency, also frequency hopping spread spectrum, a bit different data rates. But what is more important is, look at the channels. It's not 79 anymore, it's 40 channels, completely different spacing of the channels. And we have 3 specialized channels for advertising and 37 general purpose channels. So you see that that is a different physical layer. So it's not compatible. No way. Okay, the chips, just if you want to look into what can chips do today, this is an example of a brand new one. And these are the chips you can use for this direction finding. I explained to you this with the headsets and the 3D stereo audio. And this is what you can do. You can also track something real-time locating systems to track goods somewhere. If you have a huge place with thousands of objects, you can track where they are. So this is quite interesting how this is done. So real-time locating, it's quite important. Here, Bluetooth Low Energy operates in a different way, where you say, okay, we have so-called events on the physical channel. And what is the most important and the new event? Again, you don't have to remember all these events. It's just the idea. And this is the advertisement. So communication can happen now in advertisements. You don't hear the term pairing first, setting up the connection, etc. No. It's just that you advertise something. So you send, as the so-called advertiser, some data on an advertising channel. Everyone knows that we basically have these 3 advertising channels, and then we can simply transmit an advertisement, and then maybe someone receives, that's called the scanner, and may answer, or yes, so you can do it or not. And that's the idea. So you have advertising channels, so scanners can listen for these 3 advertising channels, and then you can receive, immediately answer, and that could be the whole advertising event. And that's enough to transmit some data. That's way more simple. To transmit some bytes, you can do it like this, and that's all about it. Yes, you can now, based on this, do a lot more. Setting up connections, and you ask, yes, this is basically how to bond, how to pair then devices to set up a Piconet. But you don't have to. So the basic idea is Bluetooth Low Energy allows this very short exchange of data. For these beacons, for example, they just say, hey, I'm here, or whatever, some sensor values, things like this. You don't have to set up this kind of pairing where you set up whole Piconets. You can do this. You can use this to set up real connections. And that was the idea, that you have advertisement that lead to connections. It's called then a connection event. Again, you don't have to know all these names. But just to give you the idea what the difference is. And then you see master slave. And then you can do the frequency hopping. Different frequencies, 37 frequencies. But again, frequency hopping to avoid interference. And so then we have this master slave setting. Then we have basically this idea of a connection and the idea of a Piconet. It's not the same Piconets. And yes, indeed, then you can, if you do this, you can then on top set all these mechanisms of how you pair the devices. But that's basically on top of that, because first you have to set up this Piconet, the hopping, and then you can do these higher layer things. Same for the classical Bluetooth, where you first have to synchronize to the hopping pattern, and then you can do all this higher layer stuff like the pairing, bonding, whatever then it's called. I don't know why different names are used, but maybe to distinguish a bit between the different types of networks. And you see here it's called a Piconet, but it's not the Piconet we have in the classical Bluetooth, because although A is the master in its Piconet A, this is not a synchronized Piconet in a way that the slaves B and C follow the same frequency pattern. They do not share the same frequencies. So it's called a Piconet, but you have two different networks controlled by the master. So yes. You can join others like the D. First it's a group and then it's joining, then it's also part of the Piconet, things like this. So the basic idea I wanted to show you that Bluetooth Low Energy uses a different physical layer, especially because you wanted to have a more efficient way of transmitting data compared to this. You have to pair devices, you have to do the authentication, and then you have this type of connection, and then you exchange data. Yes, that's okay for a headset, but not for a beacon or for a sensor that just you pass by and it just transmits some data, whatever, in a supermarket. You don't want to pair there. You also don't want to pair with the Corona app or something like this. There you just exchange some data, measure the signal strength. That's the idea. So is there an equivalent to services and all the characteristics in classical Bluetooth? So services in classical Bluetooth, you mean the connections, or then in the end the profiles offering certain services? So that's basically what you can offer in the classical Bluetooth, that you have this whatever audio profile offering certain services. There, if you mean it at a lower layer, yes, there's exactly something like a connectionless service and a connection-oriented, called an isochronous connection. So the ACLs and something similar to the SCO connection. So there is an connectionless and connection-oriented services. So also on the lower layers, they have similar services. And if you check, this is really going too far, if you check in the standard, you will see that from the higher layers on, the protocols, Bluetooth Low Energy and Bluetooth, the classic Bluetooth use, are the same. So in the protocol stack, they have more in common. It's just on the physical layer and part on the link layer, they are different. So different mechanisms. But you will also find this connection-less and connection-oriented services and all these things. For the detail, you have to check the standard, which is confusing to, I have to admit, because they mixed this low energy into the classical standard to have one common Bluetooth standard. But by reading, you will notice that this paragraph, oh, this is valid only for the classical, oh, this paragraph now is valid only for low energy, and this paragraph is valid for both. And you will find this many, many times in the standard, that they have to explain which part of the standard belongs to which of the Bluetooth things. Okay, you debug the Broadcom chip. Okay, yes, and this is confusing. Sorry, I don't want to confuse the other participants. Just to give you an example, we had to do with patents related to Bluetooth, and inside the patent, it was a Bluetooth Low Energy patent. It was argued that there's some mechanisms, and the mechanisms they integrated were classical Bluetooth mechanisms. So even people writing patents, they confused some of the mechanisms from the classical Bluetooth with the new one, and so in the end, this was all very strange and not even a patent. But okay, that's a different story. But also for me, I have to say, this is when you read this standard, it's sometimes you think, why? Okay, this is low energy only, so okay, this doesn't apply. Oh no, this is the classical one, then it applies. So they write this in the standard, but you notice that it's kind of a fused thing by two different things. So, okay. And if you have experience debugging chips, yes, okay. Then you know way more than what I expect you to know. It's for you, for everyone here, not really deep into this. Please, you should know the basic characteristics, not these very details. Is advertising what's called pairing connected to a new device? Well, advertising you don't pair. So pairing, that means in the classical Bluetooth terminology that you enter, let's say, a secret on both devices, and then those two devices trust each other. Then you are paired. Advertising goes without any trust. Advertising is just, hey, okay, that's exactly so right. Hey, here, that's me, take this. So the advertiser sends data on an advertising channel. If someone is listening or not, well, okay, that's a different story. So you don't have to trust. So there's so pairing is basically setting up some certain level of trust, and this is why you enter a secret key. Okay, sometimes 4x0 for headsets or whatever. Sometimes nothing, you just hold the devices close to each other, or in cars you can pair, for example, new devices for some cars when the ignition is on but the engine is not running. So there's only a short window when pairing is allowed, all these things. This is just to establish trust. In Bluetooth Low Energy, for the advertising, you don't need trust. For setting up connections, etc., that's a different story. So you cannot simply set up connections to everyone. But here and that's the special thing about BLE, to have this very easy, very lightweight way of exchanging data. Okay, you see many ideas here, and that's exactly the same when we basically go to other technologies. But first this. Okay, so major changes, I think I explained this. So it's basically, if you're interested, look mainly at the physical layer. That's a different physical layer. And yes, then some of the procedures of the higher layers. And in the end, for the applications, you can do different things. That is true. But that's what I explained. So for example, for advertisements, how do devices find each other? I did not explain this on purpose in Bluetooth. In Bluetooth, there are standardized hopping sequences devices can listen to, and if they find them, they recognize, these are the hopping sequences, and then I can synchronize, etc. But here it's simpler. How can you find another device in the very beginning in Bluetooth Low Energy? You search for advertisements. Exactly. So the point is, you don't have to search for all 40 channels, all in the classical Bluetooth, scanning 79 channels or whatever. No, well, classical Bluetooth also does not scan 79 channels. There are certain hopping patterns on certain specific channels. But here it's way easier. You search for advertisements and you have 3 predefined advertisement channels. So it's not that you have an arbitrary number of advertisement channels. Just to show you, here I have it. Bluetooth Low Energy has predefined advertisement channels, and that is the idea. So the advertisement channels, they are used. You have to check them. There can be some other advertisement channels then used after this. So the other channels are more general purpose channels for data and for other advertisement. But then you can check what's going on. And if you're not interested, well, okay, so there are so many advertisements. Just walk down the street and read the advertisements, different signs you're not interested in. But if you're in, well, you have to at least receive. You have to read them. And then, exactly as you're right, okay, you check what's there, and then if you're interested in something, then the story continues. If not, then you're not interested. So that is the idea. Two different amplitudes per channel in low energy. This is a figure I have from a PhD thesis that covers the interference. And does anyone know why low energy has different amplitudes? Well, look in the standard. The physical layer offers some more options. Not interesting really for us. I have to be honest, I have to look this up as well, when you use which signal power. I'm not the physical layer person that I know all the details here of when you use which signal power and which amplitude. And this is normalized anyhow, because the wireless LAN output power is different from the low energy output power, different from the basic rate. So I have to look this up. Unless someone knows the two different amplitudes. Okay, but this really goes into detail. So the idea here is you listen to advertisement channels, you find advertisements, and then you continue. The Piconets I explained. So the Piconets, you should know in the classical Bluetooth, you follow the synchronization. Well, you follow the hopping pattern. This is how you do the synchronization. So you have to know the address and the clock of the master. Then you follow this nice hopping. Bluetooth low energy, I explained this with the help of the figure, so I answered this already. Basically, that Bluetooth low energy also knows Piconets, but the slaves, they do not share the same frequencies. So the master tells the slaves hopping patterns, but they don't have to be the same. So you don't have to, they are not synchronized, B and C in this case. We have fewer channels, so it's the same name, but it operates a bit a different way. That's all. So, but what is really more important, and this is something you should know, is why now? We discussed this just minutes ago. Why can low energy devices transmit faster? Why can you react faster? Yes, there's no need for connection setup. There's no need for connection setup. That's the answer. Now I know the reason for the two signal strength. It's always a good idea also for me to read the own slides. Yes. The point is different versions. So Bluetooth low energy came out with the version 4.1 and 4.2. That was the starting point of Bluetooth low energy, and you see how it changed with Bluetooth 5. So that's the whole story. This is why you have the different signal output powers. So that's the whole idea. So you can go up to 20 dBm, not only up to 10 dBm. So dBm, again, we try to avoid going too much into electrical engineering. That's relative signal strength compared to the output of 1 milliwatt. And then you can say, okay, how strong? Is it a 10 milliwatt? Is it a 100 milliwatt sender? Okay, so basically the newer versions can send with a stronger signal. So it's always good to read their own slides. Sorry. Okay, I knew there was something, but I could not remember the real reason. Okay, and then finally, collisions. We are from computer science, so where can collisions happen if you start with your Bluetooth transmission? You just start, and when can we have collisions? There are many ways for collisions. Can anyone think of? Yes, increased number of devices sending advertisement. That's one thing. So if you have many devices, they all send something on the advertisement channel every whatever millisecond, then it's quite crowded there. So that's one way. And then, well, different networks, they are not synchronized. So could be a different BLE Piconet. It also could be another Bluetooth Piconet, Bluetooth basic rate Piconet. So collisions, again, there's no guarantee that there are no collisions because there could be some other networks. Within the Piconet, again, there can be no collision because there we have the master again. And the master controls the Piconet, so nothing can happen there. Okay, you see, some of you already dig quite deep into Bluetooth low energy. For the rest of you, well, know the basic differences. Know, okay, if I read BLE somewhere, yes, Bluetooth on the higher layers, but that's a complete new physical layer. That's a different MAC scheme. We have certain advertisement channels, etc. So this is simpler. And the main idea really was not that we transmit a lot of data, which can be done. Yes, sure, you can transmit a lot of data. It's not a replacement of the classical Bluetooth, but the idea is then this short transmission of some bytes. That is some of the key features without pairing, without setting up connections. That's one of the ideas. Okay, but still, that's not all. And there are, again, competing standards. And there are as well also companies saying, yes, that there was in former times only the classical Bluetooth, and that's too complicated, and the classical Bluetooth supports only up to 7 slaves, so we need more devices, more and more. And that was one of the ideas, having additional development besides higher data rates and lower data rates. And one of the very famous standards there, that's the 802.15.4. Bluetooth started with a .1. So for the initial Bluetooth, classical Bluetooth standards, that's the 802.15.1. But IEEE does not further continue the development in the Bluetooth. This is the Bluetooth Alliance. Here it's .15.4, and the idea there was to go to very low power. And this is where I explained, okay, this is where you have Zigbee. Zigbee is one of the standards there, especially for home automation. Setting up yet another type of networks. So while Bluetooth low energy, etc., this is more like, okay, headset to laptop, keyboard, mouse, maybe 10 devices, maybe 2 devices, maybe a spontaneous transmission of a beacon. This is different. So Zigbee, they want to support many devices, very simple devices called reduced function devices, and they could be sensor, and this sensor could detect a fire, for example, and that's it, and then signals the fire to a parent node. And the parent node shown here in blue, these are routers in Zigbee, and they forward information to whatever a sink is. And if a connection breaks, there could be also another sink and then connected to the internet. And then typically you have a centralized coordinator, but you could also distribute the function of this coordinator. So Zigbee does not need this centralized component. But during typical building, installation of these networks, you have hundreds or thousands of these sensors in a building, and then typically you have a kind of a central coordinator for security settings, etc. And the idea is to have really huge networks. And you saw in the slides there are many more developments, more complex one, and not all of them successful. This is why I highlighted some of them. And then in the end, I also showed you we have a lot of problems there. Because if we have all the devices operating the ISM band, and there are some strange devices like these light bulbs, you have a lot of interference. And this is why I used here from a PhD this nice figure showing what's going on at 2.4 gigahertz. It's not that extreme at 5 gigahertz because there's no Bluetooth, but here on 2.4 gigahertz we have so many different systems and they are not harmonized. Usually not harmonized, like Zigbee and Bluetooth and whatever. And the hope is that you do not send too much data, that you will have not too many collisions. That's the idea. I showed you the idea of non-overlapping channels. This is why we need higher carrier frequencies to have more of these non-overlapping channels. You saw the different channels of the classical Bluetooth, of the low energy Bluetooth, and you see Zigbee, yet another setting of 16 channels. So there's a lot going on, and we try to avoid interference. That's the basic idea. And this is also what the questions then are related to. So when I show you so many standards, this is not to confuse you, but just to tell you there's not the single solution. And also all the scientists, researchers, engineers, whatever, they discuss what is the best solution. Then the companies and management, whatever, set in, and they have sometimes overlapping goals. They compete, and not all of them are successful. But Zigbee is quite successful, and you should know what is the main purpose. What are the key characteristics and what are the differences to classical Bluetooth and Bluetooth low energy? I bet you have Zigbee devices at home. Smart homes, exactly. Highly meshed, ultra low power. This is why, and this is what I explained in the next chapter, you have also 6LoWPAN, a protocol then for the higher layers, IP layer, that is adapted to the Zigbee so that you can use internet protocols, internet connectivity, plus this highly meshed network. The idea is also to have ultra low power, so 10 years running on a single battery. Why? Exactly, ultra low duty cycle, long battery life. That's exactly the idea. The reason is quite simple. Think of a janitor running around and exchanging batteries for all the devices every year. This does not scale. This is expensive, way too expensive. So in building automation, you expect devices running on battery at least for 10 years. 10 years without any maintenance. That's the idea. You cannot do this with Bluetooth or wireless LAN or whatever. So that is the idea. Plus a normal, building, office building, 10,000, 20,000 sensors. Today, a lot of cables. Well, that's also a problem, many cables. In the future, more and more wireless devices, like thermostats, for example, for heating. This is where you might, maybe you have one of these thermostats at home where you can control them via a central controller. Sometimes they use Zigbee, also smoke detectors. Sometimes they also use Bluetooth. Yes, it depends. But maybe for you at home, you can replace batteries every year. For big buildings, no way. Every year, that's way too often. So that is one of the big differences, and many more devices. So device density is much, much higher. By the way, the newest standards, LTE and successors, so the 5G networks, they go also to millions of devices per square kilometers. So the question is data rates of Zigbee, much, much smaller. So Zigbee is not for audio transmission. I mean, you could do something like this, because if you look at the data rate, you can do something like this, because that could be enough, the data rate. But more important is low latency. So if you have a game console and controllers, you could use Zigbee. That's one of the ideas. Not the classical Bluetooth, but Zigbee, for example. So that's one of the things you can do. Okay, you write that one of the light bulbs, the tap is powered by kinetic energy, which means that you press the light switch, you generate energy to control the smart lights. So that is really low power. Yes, then we are at so-called energy harvesting. There are companies since, I think, 20 years from now, they do this. So energy harvesting. That means you get the energy from the environment, solar panels, or just using the switch. There's a piezo element integrated, and if you push the switch or whatever, you create enough power to trigger some datagrams. And there was one company, they invented this, I'd say 20 years ago, called Enocean. They have complete battery-free devices, also sensors for windows and all these things. And they do this, and sure, you can also buy this, buy these types of devices, not following any standard, but with Zigbee at least you can create a larger network. So it's very easy to set up something like this with a point-to-point connection. But if you want to have a mesh network, then it's a bit more complicated. And mesh networks are extremely important because you might have link failures. So if there's interference, or one of the devices destroyed, then you have link failures, and then you need these mesh topologies. So that is the idea. So what you write, this is really extreme energy harvesting, but indeed that's enough. You use the switch, you tap it, and then you create enough energy, and you send some bytes, and that's it. And in this case, the receiver is connected to the mains, maybe connected to 230 volts somewhere close to the light, and this receiver is always on, waiting for just some bytes. That's it. Then you use some encryption, etc., so not everyone can send this. But indeed, so Zigbee, it's one of the technologies. There are some others as well, but that's one prominent member. Okay, some final questions related to interference. How can you avoid interference? Your wireless system, what can you do? And what does Bluetooth offer in this respect? As a user, you cannot do that much. What can the systems do without users? Well, the user can switch off all the other wireless LANs, but still you have your neighbors. The user cannot really control that much, but what can the systems do? Look at the setting here. This is a setting you have at 2.4 gigahertz. Change the channel. So if you're, for example, on one of the non-overlapping channels within wireless LAN, you can change the channel. What can Bluetooth do? If you have a wireless LAN here, what does Bluetooth do? Adaptive hopping. You see that you have up here 79 channels, so Bluetooth can then use, for example, only this set of channels. At least at the same device, because you have a device like a smartphone, laptop, whatever, with Bluetooth and wireless LAN integrated. That means that you can, for example, say, okay, I'm using the channel 1, then I avoid all these frequencies covered by channel 1, and I perform the hopping for Bluetooth only using the other channels. Then you have at least no interference close to your device. I know if you have many neighboring wireless LANs and you cover basically everything, well, you cannot avoid all the channels, but at least at the same device you can avoid this. There's another mechanism that basically switches off Bluetooth as soon as wireless LAN is sending, receiving, and then you switch it on. But this adaptive hopping, that's the way you can go. And there's even a standard how one network adapter can tell the other network adapter which frequency it uses. So that's the idea. So how to avoid the interference between Piconets, that's solved automatically. So the Piconets, they are not synchronized in any way, but what they do is they just use whatever in a pseudo-random fashion the different channels. So two different Piconets have different hopping patterns. So there may be some interference from time to time, but normally there's no interference at all. So the main problem is that you have interference between a wireless LAN and one of the Bluetooth systems. So this is also why it's a good idea to have the wireless LAN at 5 GHz, 5 or maybe in the future 6 GHz. Then you are far away from all this Bluetooth stuff and not using wireless LAN at 2.4 GHz. So that's one of the ideas, because 2.4 is too crowded. It's extremely crowded. And then you have Zigbee in addition, etc., etc. So, well, the point is 1 out of 79 for one Piconet. At one moment in time, you use indeed for a Bluetooth Piconet only, let's say, this one channel for 625 microseconds. So for 625 microseconds, so you stay on this channel. And after 625 microseconds, you jump to the next channel. This is your random hopping. So everyone is hopping all the time. So if you have a second one, you will not notice it. If you have, let's say, 30 or 40 Piconets, the same space, you will notice it, because then you will have quite often interference. So, but usually what do you have? I mean, you're sitting in a seminar room, everyone has maybe a Piconet, plus you're not sending all the time. So yes, the paired devices, they perform this hopping, etc., and that's it. So there are some collisions from time to time, but this is why we have retransmission. And that's exactly also what voice connections do, that they simply retransmit again this synchronized, this connection-oriented data. It's simply retransmitted. Or, well, you can send it several times, you can integrate forward error correction, etc. But the basic idea is you do this adaptive frequency hopping. That's at least something you should know, that Bluetooth can adapt its hopping pattern depending on which wireless LAN channel you use on your device. You cannot react on all other wireless LANs. That's not possible. Because as I told you already, here I see something like 40 wireless LANs, so all the channels are occupied. So please go to 5 GHz. Okay, so that basically concludes everything about wireless LANs, wireless personal area networks. I know that is quite a lot of material, but please go into the details if you're interested, but you should remember the basic mechanisms. So you should be able to compare. If I say something like Bluetooth, here's Bluetooth and here's wireless LAN, let's say classical Bluetooth, for example, and then how is, for example, MAC handled, or quality of service, or rough data rates. So if I ask for data rates, doesn't matter if you say 1 or 2 gigabit per second, but it matters if you say 1 kilobit or 1 gigabit per second, something like this. Okay, so that is the basic thing you should take away from all of this. Okay, time's up. If there are no more questions, then thank you all for today. And then we hear, see, read each other next week. And then next week we go up in the layers, and then we cover the more internet-related protocols. What happens on layer 3? Why do we need something? Maybe we don't need anything there. So this is something to discuss, and you will see it will be less and less content. So this is, I know it's quite a lot here. There are so many different standards, but okay. That's how it is here on layer 2. Thanks a lot, and Have a nice week. Bye.